Hello everyone, we are Team Tech Trojans and today we are presenting our solution for the problem statement Development of Radar-based Living Person Detection System for use under the Rubble. Our project is titled the Smart Rescue Probe. This diagram illustrates the complete system architecture of our Smart Rescue Probe. It's designed around three main sections. The probe head on the right, which contains our sensors, the core processing unit in the center, which is the brain of the device, and the remote display on the left, which is the user interface. Let's start with the probe head. This is the part of the device that interacts with the environment. We use a bistatic antenna configuration with two separate high-gain Vivaldi antennas. One is dedicated to transmitting the UWB pulse and the other is dedicated to receiving the faint echo. This design provides superior signal isolation, which is critical for detecting weak signals. Alongside the antennas is the GY271 magnetometer. This is a crucial fusion sensor responsible for detecting ferrous metals in the debris to help us eliminate the false positives. Next, the core processing unit. The core processing unit handles all computation and control. The heart of our system is the Corvo DWM3001 CTK module. This is a powerful all-in-one component that contains two integrated parts. First, the UWB transceiver, DW3110, which is the specialized radar chip. It generates the transmit pulses and processes the incoming echoes. Second, the microcontroller and BLE, that is NRF52833. This is the main brain, a Nordic microcontroller that runs all of our custom firmware. It controls the UWB transceiver, reads data from the magnetometer, and executes our unique sensor fusion algorithm. Now, let's look at how information moves through the system. The UWB transmit pulse originates from the transceiver and is sent out by the TX antenna, that is the transmitter antenna. The faint received echo is captured by the RX antenna and sent back to the transceiver for initial processing. Crucially, the I2C data from the magnetometer is fed directly to the microcontroller. This is where our sensor fusion begins, as the microcontroller compares the radar data with the magnetic data. Finally, the processed results like high confidence live sign are sent wirelessly via the Bluetooth link to the remote display, which is a smartphone or a tablet used by the rescuer. To validate the foundational principles of our system, we designed and successfully simulated a core pulse generation and signal conditioning circuit using the Proteus design suite. This is just a model pulse generator circuit, an advanced version of which we'll be using for our prototype or product. The heart of the circuit is built around two NE555 timer IPs. The first timer, U1, is configured as an astable multi-vibrator to generate a stable continuous clock signal, which you can see as the yellow square wave on channel A of the oscilloscope. The output from this first stage is then fed into the second 555 timer, U2. This second stage shapes and conditions the signal, creating the clean, precise, and short duration pulses required for a radar system. You can see this final conditioned output as the pink waveform on channel D. This simulation was a critical first step for our team. It proves our understanding of the core electronic principles behind generating stable timed pulses. In our final, the integrated prototype, the function of this entire analog circuit will be performed by the advanced digital pulse synthesizer located inside our chosen Corvo UWB module. The module performs the same essential task but at much higher speeds and with the nanosecond level precision required for our final UWB application. Therefore, the simulation represents our foundational design work and our successful validation of the core concept that underpins our entire project.
This video validates the three core algorithms for our Smart Rescue Probe in MATLAB: signature extraction, target localization, and signal classification. First, to overcome extreme noise, we use variational mode decomposition. Our VMD algorithm successfully decomposes a corrupted input and extracts the clean 0.3 Hz breathing signature in the final mode. This validates our core detection capability. Next, we validate target localization. Our algorithm accurately estimates the direction of arrival for multiple targets. The plot shows our estimates. The blue circles align precisely with the true direction, and the red crosses with 95% confidence intervals. Finally, to reject false positives, we use sample entropy to classify the signal. A structured biological signal like a heartbeat has a significantly lower entropy value than random noise. This allows our system to intelligently confirm a genuine life sign. These simulations prove our software's ability to extract, locate, and classify a life sign in a challenging environment, confirming that our technical approach is sound and feasible.